Hey guys, this is the next unit, vectors. Oh, it's still part of unit 8, but it's just the next application of trigonometric functions. So we're going to look at vectors in detail. I hope you guys remember this dude from that movie. I think it's Despicable Me 6. Yeah. Anyways, a vector is simply something that has magnitude and direction. So size and direction. Magnitude is the same thing as size. So for this arrow, its length would be its magnitude, or its size, and where it's pointing is the direction. So the length is the size, and the direction of the arrow is the direction of the vector. So for example, in this vector called I, it starts at H, goes towards I, right? So if you try to draw it, this is what it would look like, starting at H, going towards I. This one starts at I, goes to H, and it's written IH to represent that it's in the opposite direction. This tells us something. This tells us that the vector AB, right, is not the same thing as the vector BA, right? Because BA is opposite direction. They will have the same size, but the direction will be different. So in vectors, look out for something like that. So it starts at I, goes to H. Vectors are written with bold letters in some books. In some other books, they use a squiggy on top. This is a common notation. It's used in math, physics, science, chemistry. But yeah, it's either a squiggy or a bold letter to represent a vector. So V represents a vector with the direction and magnitude of HI. A vector with no magnitude is called a zero vector, and therefore has no direction. No magnitude, no direction. If two vectors have the same magnitude and are in the same direction, they are equal. So yeah, that kind of helps explain what I was writing here, that BA is not equal to AB because they're not in the same direction. This one goes from B to A, this one goes from A to B, not the same direction. Well then, yeah. Equal vectors do not have to have the same starting points. They only need to have the same magnitude and direction. So just like you see in this image, they don't start from the same place, but they have the same magnitude and they have the same direction. Vectors with the same magnitude and opposite directions we say are opposite. Yeah, same magnitude, opposite direction would be opposite. One last thing I want to add on this is vectors with the same direction are said to be parallel. If I have vectors that have the same direction, are said to be parallel. So imagine all of these vectors, if they have the same angle to the x-axis, which is what I'm referring to as direction in this case, if that angle is the same for all of them, then they will be parallel. When we're adding vectors, one thing I want you to remember always is the head to tail addition. I pick the head of one vector, I put it on the tail of another vector. I have three vectors here. I have the sorry, let me go together. Never mind. Oh yeah, there we go. So I have V and I have U, right? So if I want to add those vectors, V and U, I just pick the tail of one of them and put it on the head of the other, right? Head to tail addition. And then the resultant will be a line drawn from the tail of the first one to the head of the last one. So that will be the result of V plus W. Yeah, so it's just head to tail. Get the tail of one, put it on the head of the other, then draw a line from the tail of the first one to the head of the last one to get the resultant. Another example, if I was adding these two vectors, this one plus that one, right? Let me call this B and that is A. I can, either way is fine. I can pick the head of A and put it on the tail of B, or I can pick the tail of B and put it on the head of A. So if I want to put the tail of B on the head of A, I will just end up drawing it like this. right? And then a line drawn from the tail of the first one, so the tail of A, to the head of the last one, the head of B, is going to be your resultant vector. This was A, and that is B. We'll see some more examples on this. Is vector addition commutative? Yes, it is. Commutative means if I switch the order, does it change the result? For example, in mathematics, addition is commutative. 3 plus 2 is the same thing as 2 plus 3. So when you change the order, it does not change the result. That's what commutative means. So vector addition is also commutative, because if I add v plus w, I get the same magnitude and direction as if I add w plus v. Hope you can see this. Magnitude and direction will be the exact same thing. Is it associative? Let me try to explain it. In mathematics, associative means when you have 2 plus 3 plus 5, and then you work it out by first taking 3 plus 5, which is 8, plus 2, which is 10. Is that the same thing as if I take 2 and 3 first, and then add to 5? Is that the same thing? Yes, I get the same result. So that's what associative means. And in vector addition, yes, vector addition is also associative. It doesn't matter which one is coming first, as long as you're maintaining the signs of the operations. A scalar is anything that a constant number or a constant value that multiplies a vector and changes its magnitude. So a scalar, when a scalar is multiplied by a vector, it changes the magnitude of that vector, right? Sometimes it can change the direction if that scalar is negative. So if it's negative, that means that vector is now going to go in its opposite direction. So if this is your vector v, the black arrow, then v multiplied by 3 will be the purple arrow in the middle, that one. Multiplied by v will be that arrow, and it's showing you that this vector is now multiplied 3 times. Because it was going over 3 and going up 1, it's now going over 9 and going up 3. Negative 3v is the one in bluish, that color. And that one is the same exact one as the purple one, but it's going in the opposite direction. Vectors can be written algebraically with these brackets. I don't know what we're going to call those brackets. Those special brackets. This is also the same way as writing them in column form, right? But maybe just so you're writing on one straight line, they're written using these interesting brackets. So that means that this vector is A units on the x-axis and B units on the y-axis. So if your vector is 2, 3, right, which is the same thing as 2, 3 column vector, then that means that wherever you start from, you got 2 units on the x-axis and 3 units on the y-axis to locate your vector. So that will be your vector. And this is what it shows here. I have A units on the x-axis, B units on the y-axis. The vector that starts at 0, 0 is called a position vector. If any vector for a point starts at 0, 0, it's called its position vector. So let's check. Is the vector below equal to v? Is this vector equal to v? Yes, it is exactly equal to v. It's just that they have different starting positions. So whether v started from here and still went 5 and 3, 1, 2, 3, 4, 5, 1, 2, 3, will still be the same vector, right? So it doesn't matter where they start. If they have the same magnitude and same direction, then they are the same vector. Now, if you know the start and end points of your vector, you can always get the vector's position vector. I want to explain this with an example. So this might look like too much writing and it could confuse you. So let me show you on this next example. If I want to know the position vectors, determine whether the vectors are equal, u and v, determine whether they're equal. So in order for me to know whether they're equal, I'm going to check their position vectors. Right? They say u starts at the point P1 and ends at the point P2, right? So to find U's position vector, I will just subtract its terminal point minus its initial point. So I just subtract terminal point is 5, 1. I'm trying to write these crazy brackets. And its initial point, subtract, is 2, negative 3. When I'm subtracting, I subtract x coordinates together and y coordinates together. That's x and that's x. That's y and that's y. So I'll subtract 5 minus 2 is 3. 1 minus negative 3 is positive 4. So U's position vector is 3, 4. Let me do the same thing here to find V's position vector. It will be P4 minus P3, which is terminal minus initial. Oh man. It'll take me a while to get used to these brackets. Minus 6, negative 1. 9 minus 6 is 3. 3 minus negative 1 is 4. So these vectors have the same position vector, right? Same if I calculate the magnitude from this, it will be the same. If I calculate the direction from this, which we'll look at in the next lesson, it will still be equal. So these vectors are the exact same because they have the same position vector. Yes, that's the working. Can you come up with two vectors, one horizontal and one vertical, which add up to V? Let's see. A horizontal vector will just be one that only has a horizontal component. In other words, zero vertical component. So if I say that this vector here is A, then that A is going to equal 3 units on the X and 0 units on the Y. And if I say that this vector here is B, then that vector B will be 0 units on the X and 2 units on the Y. So I can now say that A plus B is equal to V, because when I add them up, I will get V, and which V is 3, 2. So the A that I was showing you earlier is called the horizontal component of the vector, and B is the vertical component of the vector. A and B represent the lengths of the X and Y components. Now in vector form, these X and Y components are commonly called I and J, and when we start talking about three-dimensional vectors, then the K comes in. This is analogous to some other notation you might have heard of X, Y, and Z. So X, Y, and Z is the 3 dimensions commonly used in physics, but in math it's I, J, and K. And these are interchangeable. So I, J, and K 3 dimensions, X, Y, and Z 3 dimensions. So when we talk of I, we mean the X coordinate, and J means the Y coordinate. So if I want to write this vector in terms of I and J, it's just going to be 7I plus 10J. That's the same way as writing vector V, right? 7I and 10J. So using these vectors, can I find U plus V minus W, vector addition? When I'm adding vectors, I simply add their X components together and their Y components together. This is I plus 5J is U, plus V is negative 2I minus 3J, and W, that's subtracting W, W is 4I minus J. So just simplifying this, I'll have I plus 5J, I'm going to take out the brackets, minus 2I minus 3J minus 4I plus J. I'll look for all the I's and add them together, and all the J's and add them together. I, negative I, negative I, so I have a total of negative 5I. And then I have J, 5J, negative 3J, positive J. So I end up with a total of positive 3J. So that is the result of adding this expression, U plus V minus W. That is the result. Given V is equal to this, can I find 3V and half of V? Yes. 3v, I'm simply multiplying this vector by a scalar. So that means I'll multiply everything by the same number. So 3v will be 3 multiplied by this vector, 2, negative 1. So that will be 3 times 2 is 6, and then 3 times negative 1 is negative 3. So that will be 6, negative 3. That's my new vector, that is 3v. And a half of v means I'm multiplying everything in the initial vector by a half, or dividing by 2. So this will give me 1 and negative a half. That is what a half of v is. Now I know that for you in your books it's going to be hard to write these things in bold. So if that's the case, you can just represent them with a squiggly on top. Squiggly on top, that means that it's a vector. Use the vectors shown to sketch what? Use the vectors shown to sketch u plus v, u minus v, and 2u. Remember head to tail addition. Pick the tail of one, put it on the head of the other, or the other way around. Head of one on the tail of the other. Now I'm going to break this apart and show that this is u. This vector here is u, right? And this vector here is v. I'm going to just put it here on its own, just so we can see what it's about and be able to work with it better. So if I want to add them, u plus v. If I want to add them, I'm going to take u as it is. I'm going to take u as it is, put it there, and then I will pick the v and get the tail of v, which is the end of v, and put it on the head of u, right? So I've put the tail of v on the head of u. Hope you can see that. I've put the tail, which is touching really nicely, but I put the tail on the head, and then if I want to get the resultant, I just draw a line from the tail of the first vector to the head of the last vector, and that line will be my resultant vector. So this is my resultant vector, which is not a very good one, but yeah, that's my resultant vector there. And my resultant vector in this case, my vector addition here has given me that u plus v is the same thing as 2I plus j, or 2, 1. You can write it like that. Alright, if I want to do u minus v, same story. U is the way it is, so I'll just grab myself a u and plant it over here. But now v is negative. V is the negative of v. Oh, I took out the v. V was here, and it was black. Now v, this time it's saying that it's negative. Instead of adding it, remember, if it's negative, it's facing the other way, in the opposite direction. So I'm just going to rearrange this so that it's facing the opposite direction, right? Same magnitude, but facing the opposite direction. And once I've done that, I'm going to pull it and put it on the head. I'm going to put its tail on the head of u. And then I will draw my resultant, starting from here, starting from the tail of u to the head of v, right? Starting from there, going there, that's going to be my resultant vector, right? And I hope you can see that my resultant vector is u minus v is equal to 1, 2, 3, 0I plus 3j, or 0, 3. Twice of u, I simply multiply u by 2. So the initial u was going over 1 and going up 2. If I multiply it by 2, it's going to double in size. So twice of u will be going over 2 and going up 4. So going over 2, going up 4, that is twice of u. Easy stuff, right? Okay, write the vector in component form. Discount how many x units it has, so that's 4I. How many y units it has, that is j. So you can either write it as 4(1), or you can write it as 4I plus j. Since it said component form, then we have to stick with this 4I plus j. Okay, hope that was helpful. This is your homework.